First, just to put things in context, in 2008, I was not even called to become an astronaut. And yes, I wanted to be an astronaut, and I still want to be an astronaut as my former director. I've done a different type of exploration. I was lucky enough to find my way in exploration, nevertheless, not having been called as an astronaut. And I had the luxury to be the flight director for the Rosetta mission. Comets have always been inspiring. Why do we fly to comets? Well, because they inspired the human being since centuries. And it was said today, we have to explore because we want to know more. We want to know what is around us. We want to know how we were born. We want to know how we formed. So this morning, there was a very interesting visualization. We saw all our universe starting from the ISS, going back. Well, comets are somewhere in between where we started this morning and when we ended up this morning with the Big Bang. Comets are surrounding all of our solar system. If we look at this image, our solar system is this part here. This is the orbit of Pluto. It's just that part. There are billions of comets as part of the solar system, but are far beyond what we believe is the boundary of the solar system. We normally set the boundary of the solar system with the orbit of Pluto. Well, it goes well beyond. It's something like that. So why do we want to study comets? Well, because we want to know more how we form, our life form, our planet form. And why do we go to comets? Well, if you look at a building, how do you know what is inside this building, inside these walls? The best thing to do is to go to the building place when the building is being built. You find tiles, pipes, tubes, electrical wires, bricks. Well, comets are nothing else than the leftover or the building place of our planets, of our solar system. This is what formed at the very beginning, and then our planets formed. That's why we go to comets. That's why we believe we can understand a bit more how our planet Earth formed, how our planets formed, and our solar system even developed further. So what did we know about comets? Well, not very much before we did Rosetta. There were several missions. One of them was the Giotto mission, was launched in '85 and flew by Comet Halley in '86. These are all what we knew about comets when the scientists decided to launch Rosetta. This was in May '85, even before this mission was launched. Someone was brave enough at ESA to decide, yes, we're going to do another mission, will be a sample return mission. We do it together with NASA. Things changed, things evolved. The sample return mission became a landing mission. NASA partially pulled out of the project. Nevertheless, it took another 10 years to convince ourselves, yes, we can do this mission. Mid of the 90s, ESA decided to put money, put 1 billion euros to fly this mission here, to go to a comet. Took another 10 years to prepare the spacecraft. And this is the end. This is the spacecraft that we launched. It's a 3-ton spacecraft. It's relatively big. This is what we call Rosetta, and this is what we call Philae. It's the lander module that detached from Rosetta and landed on the surface of the comet. These are the sidewalls with the radiators. The solar rays are not mounted here. This was 3 tons, a bit more than 3 tons at launch. This is the spacecraft we're talking about. Why Rosetta? Well, as the Rosetta Stone allowed our people to understand all languages the same way our scientists want to understand with this mission, with the comet, with exploring the comet, how our solar system formed. Then, well, we have the tough program in front of us. If you were an astronaut on this mission, well, this is what you had in front of you. The target, 67P Churyumov of Gerasimenko. Launched in 2004 in March on an Ariane 5. Arrival date, August 2014, 10 years flight, 6.5 billion kilometers flown. Is it a lot? Well, not very much. We on Earth, we travel much faster than what Rosetta because we are much closer to the sun. We run in the order of 10 billion kilometers here on the Earth during the same time frame. And this is the interplanetary trajectory we did in the course of the 10 years. Unfortunately, our launcher are not powerful enough to launch us straight in an orbit. We didn't want to fly next to the comet. We wanted to reach the comet. We wanted to rendezvous with the comet, something nobody else had ever done. We wanted to orbit the comet, and we wanted to land. What does it mean? We have to go on the same orbit. Same orbit, the orbit of the comet is more or less on one side, same distance as Jupiter, 5 AU. On the other side, a bit more than the Earth. It's 1.24 AU from the sun. So we needed energy. Launchers do not have enough energy. We have to steal this energy somewhere else. And this we did with planets. Many people believe that gravity assist maneuver gravity is what we use to launch the spacecraft. No, it's not gravity. What we need is energy. Gravity is a conservative field. All the energy that gives you by pulling you towards the planet, when you go away, it takes it back. So you get out with the same velocity. What we are stealing is the energy or the angular momentum of the planet going around the sun. Gravity is just the medium we have used to transfer this energy from the planet onto the spacecraft. We did 4 of these maneuvers in these 10 years of flight, such that we could accelerate Rosetta so far away that we could reach our comet and we could reach it with the same velocity. So we could actually approach it and rendezvous. I just give you one number to have a feeling of what we have done in these 10 years. On board Rosetta, when we launched 3 tons, 1,700 kilograms were propellant to accelerate the spacecraft in the course of the mission of 2.2 kilometers per second. This is the delta V we had on board Rosetta. With the planetary swim by, we achieve an equivalent delta V of 20 kilometers per second, a factor 10 more than the propellant we had on board. If we had to carry all that as propellant, then we would have ended up with a spacecraft weight in the order of 100 tons, and this would have been even more difficult to launch towards the comet. So, what comes next? Well, we come out of the hibernation in 2014 and we start seeing our comet. This is pictures taken in May last year when we were roughly speaking 2 million kilometers away from the comet. So in solar system perspective, we were already very close. We could see the comet, not only, but we could also see the comet that was already becoming active. Comet is throwing out gas, dust, and we'll see later what this means. We want to orbit a comet, we want to reach a comet, but we know the position of the comet with an uncertainty of 10,000 kilometers. Then we have to resolve this uncertainty. So we start taking pictures of the comet and doing slowly maneuvers that bring our spacecraft exactly where we want. And this is what we did in the course of May, June, and July last year. Instead of having a single orbit insertion maneuver next to the comet and risking of having everything wrong, then we started slowing down relatively mildly towards the comet, and we had split the maneuver in several chunks. I don't go in the details of the maneuver here, I just want you to notice something. Here we go to the scale from million kilometers, hundreds of thousand kilometers, thousands of kilometers, until we reach the comet early August last year. One thing you see, we are approaching it from the direction of the sun. Why? Well, because we need to see the comet. We couldn't approach it from the backside, otherwise we wouldn't see the comet when approaching it. And we needed to see it because we didn't know exactly where it was. So we needed to do this. Then we started seeing our comet. This is July, a couple of thousand kilometers away, and we start seeing a relatively odd shape. We went closer and we found this. This is the comet we found. You see it's rotating as a period of 12 hours. It's an object which is 5 kilometers big. I come back to this later on. Where is it exactly what we were expecting? Well, not really. This is our shape model that we had prepared with the Hubble Space Telescope observation in 2003, and we were expecting something like this. We went there, we almost found 2 different bodies. For a while, we were speculating whether these were 2 bodies and eventually moving compared to each other. If this was a binary system, then we would have had serious problems. Our systems were not ready to characterize and land on a binary system. So this is the final approach. I assume, and I say I assume because I'm not an astronaut, but people that went on the Apollo, when they're approaching the moon, then they saw something similar to this, at least. You see the comet disappearing from the navcam images, the navigation camera that we have on board, exactly because we didn't know exactly where the comet was. I said we had to do maneuver, and we were continuously re-estimating where the comet was and continuously applying correction maneuver to get there. The last maneuver we did before the arrival here was slightly overperforming compared to our prediction and basically brought us completely off track. We even missed the comet from the field of view of our camera. Was promptly brought back in track, and this is the comet we found when we got there. I repeat, this is an object of, roughly speaking, 5 kilometers size, and this is where we wanted to land. The next problem is, how do we land on something like this? Find a landing place, a safe landing place, a smooth landing place on this object. This we had to tackle. But before getting there, we had to do something else. We had to characterize the comet. When you fly to Mars, or if you have a spacecraft orbiting the Earth, you fly to Jupiter, you know almost everything of these systems. We didn't know anything of the comet. First, we didn't know where it was. We didn't know its mass. If you want to orbit an object, you have to measure the mass of the object, or at least to know. We hadn't the faintest idea what the density of a comet is. We didn't know its shape. We didn't know its spin axis, whether it was spinning, whether it was nutating. The comet is emitting gases. This is ice that is sublimating because of the heat of the sun, and these gases are impinging on the large solar rays of Rosetta. This is wind, and it's blowing the spacecraft away from where it should be. So we had to characterize all these, and this is the orbits we flew at the very beginning. So this is the time when we had characterized the comet, and we managed to go down orbiting the comet itself. I just skip this one and go to the next one. Once you are there, you have to learn to fly around the comet. And I think we did nothing else what the human being did in a couple of centuries more than, we had only 6 weeks to do this. When the human being started going out of his cave or whatever, started to go around, use reference points. There was a river there, a tree there, a mountain there. These are nothing else than reference points. Well, we did the same when we got to the comet. We located some features on the surface, and these were our reference points. In every image we were taking with our cameras, we were using always the same reference points to determine the spin axis of the comet, the spin ratio, and the shape of the comet. The human being wrote maps. We wrote a map of the comet as well. This is our 3D model of the comet. On the left side, you see a real picture of the comet. On the right side, a simulated picture with our 3D model. It's our map of the comet. That's why we could fly around the comet. Then when we started flying, I mean, the human being with aircraft, we started using the basic laws of physics to say, if I'm traveling at this velocity and I travel for so much time, then I run for so many miles or many kilometers, where we applied basic physics laws also to orbit the comet the very first time. We assumed that the comet has a single point mass, all mass concentrated in a single point, but we had to measure this mass. So we used the spacecraft as a sensor, and we measured that the comet was weighing, roughly speaking, 10 tons. This is how do we do it? Well, we were flying next to the comet, and the comet was attracting us, and we saw how the orbit of the spacecraft was perturbed by this. The trajectory of the spacecraft was perturbed by this. But at the same time, we didn't know where the comet was, how the comet was rotating. So our estimator, normally when you fly a spacecraft, the problem of navigation is to know where the spacecraft is compared to the object you want to fly around, the Earth or whatever. Here we didn't even know the object, so our variables were many, many more than the usual navigation process. This is our estimator, and this is the masterpiece of navigation we had to do. This was not enough. We had to do much more. We still wanted to land the comet. This is far not enough. As we introduced radio assisted navigation on aircraft in the 50s maybe, then we had aided navigation. Our operators, instead of looking at images at the famous reference points manually, we had tools developed at the same time that could show us the real images of the comet compared to the simulated one and allow us to identify the features of the comet and know how we were flying. We went farther. Navigation also on the Earth went farther. We have the GPS now. We have satellites. By triangulation, we know where our mobile phone in our pocket is. Well, we did the same on the comet. The only thing the other way around. We're taking images of the comet. By triangulation of the reference points, by now we know where they are. We do triangulation. We know where the spacecraft was when the picture was taken. And this is all automatic on ground. So we downlink the images. We recognize where the spacecraft was. We determine the orbit of the spacecraft. So instead of global positioning system, I call this comet positioning system. And this is the history of navigation in 6 weeks. Now, I was asked as well to give you a feeling of what it means flying around the comet. Good. So I'm not an expert of the ISS, but I try to mention as well something along this line. What do you see on this plot? I could talk for an hour on this plot, but a couple of points. The green line goes on this axis, and this is the distance in kilometers of the spacecraft to the comet from July to October last year when we approached the comet. All the other curves are on this axis. These are accelerations in kilometers per second square, also logarithmic scale. So every jump here is a factor 10. Now, a couple of numbers more. Acceleration on the Earth is 1 EL minus 4 kilometers per second, so it's far above here. It's 100,000 times higher than the acceleration we were observing when next to the comet. Since we're talking about ISS is microgravity. Well, look where microgravity is. Microgravity is 1 to the minus 8, so it's this line here. So if Chris, you said this morning that in microgravity everybody is super happy, here we are talking about picogravity environment. We must be even happier if we explore something like comets and we go beyond the ISS. What did we do? Well, here, early July, you see that the distance to the comet is going below 1,000 kilometers. Look at these two curves here. This is the difference of the acceleration given by the sun on the comet and the one given by the sun on the spacecraft. By doing this difference, we call it third body problem. And this is our estimation of the acceleration imparted on the spacecraft by the comet. So the comet is attracting the spacecraft. There was a time, end of July, early August, when we got to the comet, where this acceleration took over. This is the day we could measure the mass of the comet, exactly by estimating these two accelerations and seeing the effects on the spacecraft trajectory of the comet attracting it. Then we had to go farther. We had to characterize the comet. We developed our navigation system. Another point here, we had to go much closer to the comet. At this stage, we were in the order of 100 kilometers, then 50 kilometers, then we went down to 30 kilometers, and we went farther down to 20 kilometers distance from the nucleus. What was difficult there? Well, the comet is emitting gases. I said earlier on, these gases are impinging on the solar rays of the spacecraft and blowing the spacecraft away from its orbit. So if I'm flying in front of the comet, the gas is emitted towards the sun and is blowing me away. So we went on the terminator plane. The terminator plane is the plane perpendicular to the sun direction. Why? Because I'm pointing my huge solar rays to the sun, which is there, and the gas is coming radial from the comet. It's impinging only on the edge of the solar rays. And this is what we did here. This is the acceleration given by the gases, the aerodynamic acceleration acting on the spacecraft. And you see that despite the fact that we went from 30 kilometers down to 20, the acceleration went down is because we moved from in front of the comet to the terminator plane. This is another. So we had to develop a model, if you want, of the winds that are blowing around the comet. This is almost like doing weather forecast. There's a third point here. When we went down to 10 kilometers and we wanted to land, you've seen the shape of the comet. This is not really a sphere. You can imagine that the gravity field is not particularly well shaped. So we had to model the irregularities of the gravity field. But if we are far away, we cannot distinguish them. These are the irregularities of the gravity field. This black line here, if these are the numbers, these are several order of magnitude below the other acceleration we are observing. So we cannot estimate them. But when we went down to 10 kilometers, then this value picked up. And then we could estimate also the irregularities of the gravity field of the comet. So we had to do all this in 6 weeks. Many people believe that the landing of Philae on the surface of the comet was the most difficult thing we did on Rosetta. Well, for sure it was the most attractive, no doubt. But doing this was far more difficult, far more pressure on us, and technically much, much more challenging. And it's because we have done all this that we could land on the surface of the comet. So we selected our landing site on the small lobe of the comet. This is the target point, and this is our error ellipse. Come back to this later on. This is our timeline. The landing is very passive. It's a ballistic delivery. So Rosetta, the mother spacecraft, is orbiting the comet and is releasing the lander. You see it on the top right in this animation there. This is Philae going down towards the comet. I'm not going to describe the timeline of activity we had around that time, but you can imagine that the most important thing is to deliver Philae at the right time, in the right position, and with the right velocity. Again, a couple of numbers to give you the feeling. The 7-hour descent is written here. If we were wrong at the separation point here with the velocity of Rosetta of 1 centimeters per second, propagated for 7 hours, this is roughly speaking 250 meters. So we would land 250 meters away from where we wanted. You have to understand that what we are doing here, we are basically flying over the Mont Blanc. I also, like Samantha, grew up in the Alps, and for me the comet is like the Mont Blanc. It's 5 kilometers big, it's rocks and ice, and this is what it is. We were flying with our plane, with a washing machine, 100 kilos. We had to throw it out from 22 kilometers altitude, so twice the altitude of an airliner. And we cannot make a mistake with the velocity in the order of 1 centimeters per second. Must be much smaller, otherwise we don't land where we want. So how did the landing go? Well, this is prepare for landing. So this is the lander Philae seen from the mother spacecraft. So I guess who was on the command module for the lunar mission might have seen the lamp going down, something like this. And this I don't speak anymore. These are the images of the landing. Just say that this is going in real time. So if you were an astronaut sitting on Philae, you would see the comet moving like that. Leave it, leave it. It's okay. Leave it. It's okay. Oh, yeah. Now the range is 22 meters. 15 now. We'll stop at 9. So this is the last image we've taken from Philae when going down. The resolution on the surface of this image is roughly 1 centimeter per pixel. So what you see, there are pebbles and boulders, small boulders that are on the surface. Now, most of you for sure know that something went wrong. When we went there to look where Philae was, then we found this footprint, and Philae was not there. So before we look into where Philae is and what happened afterwards, I think I don't say anything completely wrong if these two footprints are comparable in the history of space exploration. Now, what happened on that day? Well, this is where we were left. Our target point, our error ellipse, roughly speaking, 500 meters in radius. This was the very worst case. We never wanted to come even close to that. And this is where Philae touched down, was 110 meters away from the target point. So you might imagine that our error in velocity at separation was in the order of 1.7 millimeters per second of an object orbiting another object at a velocity of 30 centimeters per second, both traveling at 15 kilometers per second in the solar system at 500 million kilometers away from us. This is what we have done on that day. Philae did an anchor. We saw it flying away. This was the last point where Philae was observed in flight. When after it bounced on the surface, the anchoring system couldn't anchor. Basically bounced away. The gravity, we're in a microgravity environment or picogravity environment if you want. So Philae was flying away, went up to 1 kilometer's altitude and landed somewhere else after having tumbled a couple of times on the surface of the comet. We know that Philae is somewhere there. We perfectly know that it's there. We haven't seen it yet. We do not have a single image that tells us Philae is there. Philae operated for 3 days on the surface of the comet and started sending us fantastic images. This was already shown by Jean-Jacques. This is the scientist that basically is responsible for this camera, says this is 80 centimeters away from my camera. My camera is 20 years old. This is 4.5 billion years old. So this is what we have been doing with Philae. This is another image of another rock close to Philae. It was in the dark, so this is largely stretched, the image, and you see the cracks and the rocks that are there. The comet is not only Philae. The mission is not only Philae. The main scientific mission is Rosetta itself, the orbiting spacecraft. Philae lasted 3 days, did its own operation, and what we did is basically we continued operation. We managed to fly even closer to the comet. The image here is taken from a distance from the surface of roughly speaking 6 kilometers, so you see several details. And what you see here is a video of this close flyby. What you see, this is the shadow of Rosetta on the surface of the comet. So we managed to capture, we flew the subsolar point and we managed to capture our own shadow, something I would have never believed would be possible. Now, the comet becomes more active, it gets closer to the sun and it starts throwing out more and more gas. At the beginning, when we reached the comet, we were measuring 3 kilos per second. Now we are measuring in the order of 300 kilos per second. This is all dust and gases which are coming out of the comet. And you see the jets here in this video taken by the OSIRIS science camera. These jets are disturbing the trajectory of the spacecraft, but not only, there's much more coming out of the comet. There are boulders coming out of the comet, so the comet is sort of cracking and modifying itself. So we keep track of these things. Next year we want to fly closer to the comet when it will go again away from the sun and we want to explore it. I want to show you one last image. This is a snowstorm. This is what the star sensors of Rosetta sees in the sky when it's flying in the environment of the comet. So you can imagine that there's an environment that is very, very active. It's not easy to distinguish the stars in something like this. And these are the dust particles that one of the instruments has collected. So dust particles are continuously hitting the spacecraft. We are collecting them and they are exploring them. So this concludes my presentation. I have the selfie of Rosetta. I have another picture of Rosetta with a massive jet we observed only for a few minutes on the surface of the comet. The mission is still very active. We want to, as I said, we want to continue till September next year, and we want to go even much closer to the comet, and we will land the spacecraft on the surface of the comet next year. So stay tuned. There might be much more coming out of this mission. Thanks a lot for your attention.